In this video, we are going to discuss about the color in coordination compounds. We know that coordination compounds are capable of showing wide range of colors. Now, when you pass white light to a coordination compound, that coordination compound will absorb radiations of certain wavelengths so that the light that comes out will no longer be white in color. And we say that the color of the complex is complementary to that which is absorbed. So what we see is the complementary color. Now what do you mean by complementary color? Complementary color is the color generated from the wavelength left over. Means when you pass this white light through the compound, some colors are absorbed whereas some are not. So we see the color which are not absorbed, or we see the wavelengths of the color which are not absorbed by the coordination compound. For example, if green color is absorbed by the coordination compound, then we see the compound as red, because red is the complementary color of green. Now next, let's see an example for the color of coordination compound. And what is the reason for the color of coordination compound? The question is TiH2O 6 times 3 plus is violet in color. Why? Now TiH2O 6 times 3 plus. Now any question related to color if asked, you have to write the explanation on the basis of crystal field theory, because the color in coordination compounds is explained by crystal field theory. So TiH2O 6 times will be X0. So X will be equal to plus 3. So titanium is in 3 plus oxidation state. Now titanium 3 plus, what is the electronic configuration of titanium? Titanium is argon 3d2 4s2. Now titanium 3 plus means it will be argon 3d1. Now if you write the electronic configuration and the base of CFT, it will be T2G1 Eg0. Now there is one electron in the T2G orbital. Okay, now what happens when you pass? Now here it is said that when you pass light through this complex, it absorbs wavelengths corresponding to yellow-green region, and the color, complementary color that is produced is violet. So what happens on absorbing that yellow-green wavelength? The electron present in T2G orbital gets excited and it goes to high energy Eg orbital. So what will be the configuration on absorption of radiation H nu? It will be T2G 0 Eg1. Okay, so now what happened? The electron got excited and we see the complementary color of the light absorbed, which is violet. And also you can see that there is a movement or excitation of electron from one d orbital to another d orbital. So we can also say that dd transition has taken place. dd transition. So this word is very important. The color of coordination compounds is due to dd transition. That is, the electron present in one d orbital got excited to higher energy level. It's also a d orbital. So we have dd transition possible in coordination compound, which is responsible for its color. Now if there is no ligand present, then no dd transition is possible and splitting of orbitals will not take place. So what happens? No color is observed. Now example I will give you. TiH2O 6 times Cl3. This compound on heating will lose water molecule, which is the ligand, and the compound will become colorless. Now another example, CuSO4 is colorless, whereas CuSO4.5H2O is blue in color. Why? Because CuSO4.5H2O means that water molecule will act as a ligand. So it is blue in color, whereas CuSO4 means there is no ligand, which means it is colorless. Now, the influence of ligand on the color of coordination compound can be studied with the help of an example, that is the reaction of NiH2O 6 times 2 plus En. Now, En is ethane 1,2-diamine, it's a didentate ligand. So, I am going to replace this ligand H2O with En. You know, it's a didentate ligand. So, what happens? 2 water molecules will be replaced by 1 En. Now, I am going to write the product formed. It will be NiH2O 4 times En 2 plus 2H2O. And the color of this compound is pale blue. Now, in the next step, I am going to add to this pale blue complex, that is NiH2O, and this complex NiH2O 6 times is green in color. Now, it changed into pale blue. Now, NiH2O 4 times En 2 plus another En is added. So, the formula will be NiH2, again 2H2O will be substituted. So, NiH2O twice, En twice, 2 plus 2H2O. Now, this compound is purple in color, blue or purple in color. Now, next we have 2 more H2O which can be replaced. So, NiH2O twice, En twice, 2 plus En. So, it is H2O is replaced, all H2O is replaced. So, it will be En thrice 2 plus 2H2O, and this is violet in color. So, you can see the presence of ligands, the change in the number of ligands or the change in ligands will also produce a change in color of the compound. You can see the different colors given when NiH2O 6 times 2 plus, which was green in color, is treated with ethane 1,2-diamine. Okay. Now, next we are going to do few questions based on crystal field theory. So, the first question is, aqueous copper sulfate solution gives green precipitate with aqueous KF and a bright green solution with aqueous potassium chloride. Now, here it is given aqueous copper sulfate. Aqueous copper sulfate is blue in color. Now, you can say aqueous copper sulfate, the formula will be CuH2O 4 times SO4. Now, this when treated with potassium fluoride, what is the compound that you get? You get H2O getting replaced by F minus. So, it will be CuF4 SO4, and this is green in color. Now, again the second question is, we get a bright green with aqueous potassium chloride. So, treat this with potassium chloride. What is the product formed here? H2O will be replaced by Cl minus. So, it will be CuCl4 SO4, which is bright green in color. Okay, so the change in ligand will produce a change in color of the complex. Now, the next question is, this is a very important question. A solution of NiH2O 6 times 2 plus is green, but a solution of NiCN 4 times 2 minus is colorless. Explain. Now, I am going to take the first compound, that is NiH2O 6 times 2 plus. This is green in color. Now, let us find the oxidation state of nickel in this. Nickel, X plus 0 is equal to 2 plus, means nickel is in 2 plus oxidation state. Now, what is the electronic configuration of nickel? 3d8 4s2. Now, here 2 electrons are lost, so Ni2 plus will be 3d8. Now, we have to write the CFT configuration. You draw the diagram. Before you draw, you check the coordination number, it is equal to 6. So, we have T2G, Eg. Now 8 electrons means 1, 2, 3. Now this is a weak ligand. So you can say no pairing, which means the electrons will go into Eg first, followed by pairing. So 5, 6, 7, 8. Now what will happen? Here you can see this crystal field splitting, that is delta O is small. So what will happen? DD transition is possible. So this compound is colored. What is the color? Green color. Okay, so this is very important because you will feel that there is no electron to get excited. But in this case, since delta O is small, these electrons in Eg can come or T2 can go up like that, and DD transition is possible, and this complex is green in color. Now, the next question is NiCN4 times 2 minus is colorless. So I am going to write that compound. NiCN 4 times 2 minus. This is colorless, which means let's find the oxidation number of nickel in this. Nickel is X minus 4 is equal to minus 2, X will be plus 2. So nickel is argon 3D8 4s2. Here nickel is in 2 plus oxidation state. So again it is 3D8. Now let's draw the CFT. Now here the coordination number is equal to 4, means who will be in the lower level? We have E, and higher energy we have T2. Now 3D8, so 1, 2. Now here it is cyanide ion, which is a strong ligand. So first pairing takes place. 3, 4, 5, 6, 7, 8. So this is E and this is T2. Now in this case, since it's a strong ligand, what you can write? It's a strong ligand, so this value delta O or crystal field splitting is very large, which means what is not possible? No DD transition is possible. So the compound is colorless. Okay, so very important in this case, since delta O is very large, no DD transition is possible and the compound is colorless. Now the next question is FeCN 6 times 4 minus and FeH2O 6 times 2 plus are of different colors in dilute solution. Now why are they of different colors in dilute solution? Due to different ligands. In FeCN 6 times 4 minus, the ligand is Cn minus, and in FeH2O 6 times the ligand is H2O. So since the ligands are different and Cn minus is a strong ligand, means it can cause high crystal field splitting, whereas H2O is a weak ligand, so small crystal field splitting. And also DD transitions are possible in both the complexes, so they are of different colors in dilute solutions. Okay, so you have to write DD transitions are possible. Now there is one more question. This is the question. What will be the correct order for the wavelength of absorption in the visible region of the following? NiNO2 6 times 4 minus, NiNH3 6 times 2 plus, NiH2O 6 times 2 plus. You have to arrange this in increasing or decreasing order. Which order? For the wavelength of absorption. Okay, so first let's see on the basis of ligand, how can you arrange them? Who has the highest field strength? Which ligand is a strong ligand among this? Among this you can see, I'll write here answer, the order of ligand. The order of ligand is, the order is, I'll write in decreasing order. NO2 will come first, I am writing only the ligand. So NO2 minus greater than NH3 greater than H2O. H2O is the weak ligand. Now you know that if the ligand is strong, crystal field splitting energy will be strong. So next I am going to write the order of crystal field splitting energy order. That also will be the same, that is NO2 minus greater than NH3 greater than H2O. Now, you know that according to Planck's quantum theory, E is equal to h nu or h into c by lambda. Now, you know the relation between energy and wavelength, they are inversely proportional. So, crystal field energy, splitting energy is in this order means what will be the wavelength absorbed in the reverse order. So, what is the order? Who will have the highest wavelength absorbed here? H2O. So, the answer is Ni H2O 6 times 2 plus. This is the order. Which order? On the basis of wavelength absorbed will be greater than Ni NH3 6 times 2 plus will be greater than Ni NO2 6 times 4 minus. So, this is the answer, final answer, and this is the order in which order? Wavelength absorbed. Wavelength absorbed. Okay, so the questions are over. Now let's see the limitations of crystal field theory. Now the main limitations of crystal field theory is that the main limitation is the crystal field theory does not take into account the covalent character of bonding between the ligand and the metal atom. Okay, we know that crystal field theory considers the ligand metal bond to be ionic. It does not consider about the covalent bonding. Also, we can say that the ligands are point charges according to crystal field theory. So, it follows that the anionic ligands should exert the greatest splitting effect. Okay, since they are considered as point charges. But the anionic ligands, you know the spectrochemical series, the anionic ligands are actually very weak ligands and they show weak crystal field splitting. So, that is also a drawback of crystal field theory. So, these are the two limitations of crystal field theory, and with this we complete crystal field theory of coordination compounds. Thank you.